We'll talk a little bit about how to use a lot of what we saw today with the different I/O libraries and such, and see how to understand and tune HPC I/O performance. So yeah, we've heard a lot about the HPC I/O stack, starting with high-level I/O libraries like HDF5 and PNetCDF. We've heard a lot about different file systems, whether it be Lustre, GPFS, and also a little bit about different storage hardware. So the point being that the HPC I/O landscape is both deep in terms of the depth of the stack, but also vast in terms of the types of technologies you see at each layer. So this creates an environment that makes it kind of difficult to understand I/O behavior, and even worse, it makes it difficult to kind of inform different tuning decisions you might make as a user. So we've already heard a little bit about Darshan, which is a tool that you can use to help better understand your I/O workloads. It provides a lot of different stats across multiple layers of the stack that you can use to better understand what's happening. So it's not focused specifically at a single layer, but you can use Darshan data to kind of get an intuition about the entire behavior of the stack. So we'll step through just a couple of different layers here to give you an idea of the type of information that Darshan's capturing. We'll start at HDF5, or we'll start with the data model support layer, where we'll focus on HDF5 here. So Darshan does currently have HDF5 instrumentation for recent versions of Darshan, so starting with versions 3.2.0. I will point out that by default, this is not enabled on the data system that we have. So this is something that if you were interested in using, you'd have to install yourself on that particular system. But types of information we capture is things like what files and data sets are accessed by an application, different types of operation counts, so how many times files or data sets are opened or read or write, total read and write volumes to data sets. We capture information on common access info. So this includes details about the hyperslab accesses for HDF5. We capture chunking parameters that users may have used. And we also capture data set dimensions and total size to give you an idea of how big a data set is. And we also capture information on how HDF5 is using MPIO. And we also capture various I/O timing information. The transformation level, this is MPIO, is kind of converting from the application level data model support to something that will give you performant POSIX level access. At MPIO level, we're capturing, again, operation counts like you'd expect. We're capturing details on whether collective or independent I/O is used to particular files. And we, again, capture information on read and write volumes and more information on common access sizes used by the application. So that's just common access sizes, but also entire histograms of all of the operations that an application issued. And again, more I/O timing. POSIX layer, more operation counts, read-write volumes. File alignment is one that we'll touch on here in a little bit as a useful parameter that we capture here. And we capture more information on common access sizes as well as strides. So stride is basically the distance between consecutive I/O operations on a given process, and that can give you information about whether how big of jumps you're making in between consecutive accesses, or whether you're seeking around randomly or things like that. And again, more I/O timing at the POSIX level. Also, we have a Lustre module that gathers details on Lustre parameters. So this includes the total number of data servers and metadata servers on a given Lustre volume. Also details on stripe size and stripe width, which we've seen today as a key parameter that you should keep in mind. And we also have the complete OST list that's serving a file in case that's useful. So we'll look a little bit closer at some different examples of tuning I/O performance in this stack here. So we'll start at the bottom with the parallel file system, and then we'll kind of work our way up through different levels to show some different scenarios. But for the parallel file system in particular, we've, like I said, we've heard a lot today about how it's something that you should keep in mind as a potential tuning knob for you guys as users. So one thing that you really want to do is ensure that whatever storage resources you need for your application, you need to make sure those match your application needs essentially. So for parallel file systems like Lustre, we've heard that users do have direct control over striping, which can, so the bad news is that, as you guys are kind of finding out, it does require some effort on your part to better understand how these systems work and what kind of knobs they have and things like that. But the good news is that you can often get much higher I/O performance by being a little thoughtful about this stuff, because file systems aren't perfect for every workload, so a little bit of exploration on your part can pay big dividends sometimes. So we'll look at a scenario here, but the high-level takeaway is that you should be making tuning decisions independently for different classes of files. So for instance, if you had a simulation that has a ton of bulk data, so it's like climate data or some other large data set that they're using, that requires you to be kind of mindful about how this is stored on storage servers. So you could naively store, from 4 processes, just in this small example, all the data on a single storage server. That's pretty simple, but creates an obvious hotspot that is not totally surprising that this is not the way that you typically would want to store a massive amount of data, because then every single process is talking to the same exact storage server, and it's just really inefficient. So what you would instead prefer to do is to kind of allocate more storage resources for these processes so that they can kind of load balance across the aggregate storage resources that are available. So in this case, we just show four different OSTs, but keep in mind, you don't necessarily need to have an OST per process. It's not the way it works, but it's just kind of the way I depicted it here. But the big takeaway is that large application data sets should be ideally distributed across as many resources as possible. On the other hand, smaller files often benefit from just being stored on a single server. Fragmenting them and storing them in different places so they can be brought back together and reassembled is not really a great idea. It's a waste of time, basically. So in this case, you would rather have your simulation clients read just from a single storage server for small files. But there's actually an additional optimization here, which I think I've seen some similar thought processes in other slides earlier today. But essentially what you would have is a single process read the data from the storage system and then communicate that data out to everyone else using MPI instead. And the reason for this is it's another bottleneck just to have every process just go to one server to get even a small configuration file, because they're all kind of hammering on the same server. And oftentimes, or pretty much the case at HPC facilities, that the fabric that connects your compute node processes is much faster, so it's a lot cheaper often to share information with that where you can, especially in cases like this where a single process could easily gather all of the simulation configuration information it would need. So I'll give we'll step through some Darshan data here that kind of demonstrates the importance of matching storage resources with what your application needs. So the warning here is just be aware of what file system settings are available to you, and don't assume that they're always the best. You might be surprised to know that ALCF Theta and Nurse Corey Scratch file systems both default to a stripe width of 1. So anytime you create a file on those systems and don't do anything explicitly, they're going to be stored on a single storage server. That's probably not what you want, generally speaking. So we looked at some Darshan output from a really simple 10-process, 10-node workload on Nurse Corey's Lustre Scratch volume. And this is just like a really simple shared file workload where each process is writing a chunk of the file. And essentially, each process is writing 100 megabytes for a total of 1 gigabyte of data. And you can see here that just in this default configuration, it takes 6 seconds and got 210 megabytes per second performance. At the very bottom, you can see a snippet of the Lustre stripe settings we captured with Darshan. You can see that the stripe size is 1 megabyte and the stripe width is 1. So that kind of confirms that the default here is a stripe width of 1, so just one storage server. In this case, it's storage server number 100. I think you guys saw this command earlier, but if we use this LFS set stripe command, we can change the stripe count from 1 In this case, I just changed it to 10. I can't remember exactly how many storage servers are here. This is not striping across every single available storage server, but it's just more than one, so it's useful to see what the performance increase is. In this case, just this simple command before running your job lowered the runtime by 50%, gives you 200% performance boost as far as bandwidth goes. And you can see that Darshan's able to reflect the different stripe settings here at the bottom. So still a stripe size of 1 megabyte, but we're striping this over 10 servers and gives us a pretty big performance boost actually for a really kind of small toy workload. So you can imagine as you scale up how important this might be. Next we'll move up to the POSIX level API. So we've heard a lot about POSIX today. It's definitely an important part of HPC, obviously. It's kind of the lowest common denominator. Like pretty much every application is, at this point in time at least, funneling through POSIX ultimately. So it's an important interface to get right from a performance perspective, but it can be pretty challenging. So an example of this is file alignment, which I've heard kind of a little bit about today, but essentially file systems really kind of prefer their accesses to be aligned on certain block boundaries, or else it just kind of creates inefficiencies in how they retrieve data. So alignment is something that's often kind of important at the POSIX level. And we'll kind of, or as just to kind of visually just depict this. So on the left side here, this figure is showing what unaligned IO requests might look like. So you have a file with the different blocks that represent stripes here on this Lustre file system. And you can see that each process is essentially offset and accessing data from from 2 blocks at a time. And what this kind of boils down to at the bottom is that each process is basically talking to both storage servers. So it's creating a lot of contention across the processes to get the different chunks of data from each server. And again, this can be pretty inefficient. So instead, what you prefer is your processes kind of access data on well-aligned boundaries to avoid this particular contention. So you see on the right side what it looks like when things are well-aligned is that each process is just kind of talking to a single server, and there's not this kind of crosstalk problem. We'll again step through some Darshan data to show what this looks like. So we're going to basically repeat the same exact experiment as earlier, just a really simple 10 process example showing this on the Lustre scratch volume on Cori. And we'll start with what it looks like to do unaligned access. So this is some snippets from Darshan's DXT parser output, but you can see that rank 0 is writing a megabyte of data at an offset of 0.5 megabyte. And similarly, process 1 is writing at 1.5 megabytes. So you can see how this pattern completely, it's basically accessing a couple of stripes for each process. In this case, we're able to get 310 megabytes per second performance with this. If instead we shift all the accesses down so that we're accessing entire stripes at a time and not crossing stripe boundaries, we can get a pretty decent performance boost. And again, this is a really kind of small example. This is a toy problem. So again, this is something that would probably be a little bit more problematic at larger scales. But even so, you can see you're paying probably a 20% performance penalty in this case just by not aligning your IO at the POSIX level. So yeah, this is not necessarily a fun thing to account for. It changes from file system to file system, so this is pretty painful to deal with. So as we've it's a common theme from today, but please, wherever you can, use high-level IO libraries. Don't necessarily try to reinvent the wheel. I'm sure some of you will have to get comfortable with POSIX at some point, but generally speaking, things are a lot easier if you can kind of utilize these high-level libraries like HDF5 and PNetCDF to mask a lot of this complexity. I'll move up to some high-level optimizations, and this time I'm using HDF5 as an example. So I'm going to focus on chunking first. So if you recall from Scott's talk, HDF5 has this chunking mechanism that allows you to kind of control how data sets, portions of data sets are mapped into contiguous chunks in the underlying file. So what this allows you to do is if you have some kind of understanding of how your application is accessing data stored in an HDF5 data set, you might be able to tune the chunking parameters so that you can get bigger, more performant accesses and get the data out a little bit faster. And we'll show what this looks like with those series of different figures here. But essentially what HDF5 does by default is it'll store all of your dataset data in row major form. So it'll store all of row 0, all of row 1, all of row 2 consecutively like that, which is fine. But the issue comes about whenever your application might have another access pattern that doesn't really kind of match well with that. So if you could imagine an application that wanted to read columns of data at a time, or if it wanted to do a block-based decomposition and read blocks at a time, this doesn't really match well with how HDF5 is storing the data in the file. And it leads to some inefficiencies basically because you're having to do smaller and smaller I/O accesses essentially, and you're moving around in the file a lot. So this picture kind of demonstrates this in the bottom left, but essentially with no chunking and using this block-based decomposition, just focusing maybe on the blue process, you can see that the solid line is basically a contiguous I/O access, so it's able to read one contiguous chunk that's pretty small, and then it has to seek, which is the dashed line there, to the next part, and then read that small chunk. And then you can see how this could be kind of problematic, especially in larger data sets. So for an example here, we're going to look at a 256 process 16 node example, where each process has essentially a block of the data set, just like is depicted here, just at larger scale. In this case, each process is writing a 2K by 2K block of a data set, which comes out to exactly 32 megabytes per process. And so we'll look at some Darshan results here for what this looks like with no chunking. You can see it takes 143 seconds and only gets 58 megabytes per second performance, which is pretty bad. You can see in the bottom left corner the plots there, the I/O operation counts, and all of this is kind of grabbed out of the Darshan job summary tool that we discussed earlier. But essentially you can see that there's 500,000 plus write operations issued and 500,000 plus seek operations issued. So you can see how there's tons of I/O accesses and tons of moving around in the file to get to the right spot, basically. And you can imagine how that can really kind of bring your performance down when you're basically issuing hundreds of thousands of really small, in this case 16 kilobyte I/O requests. If instead we apply chunking so that all of the blue processes data is stored contiguously first and all of the green processes and so on and so forth, then instead you can read all this data in one contiguous chunk and not have to worry about this small I/O and non-contiguous I/O basically. So looking at the Darshan results for here, just by applying chunking that matches our access pattern, we can bring our runtime down to 52 seconds and get our bandwidth up to 160 megabytes per second. So we see almost a 3x performance increase just from enabling chunking along the lines of our expected access patterns. An alternative optimization that doesn't really have anything to do with chunking is collective I/O, which we've heard a lot about. So in this case, we're going to, instead of using chunking, we'll use collective I/O to see how that affects the performance. And again, this is just kind of repeating stuff that we've heard a lot from Rob L. and from other speakers today, but MPIO is kind of really smart about how it chooses different parameters related to collective buffering and things like that. And specifically for different file systems, it has different strategies. But the idea here is that you use collective buffering algorithm to not only generate really, really large chunks of or I/O accesses, but you also use it again to limit the number of processes that are accessing the storage system at a given time. So it's a little harder to kind of visualize what collective I/O looks like, but essentially what you have is, again, these aggregator processes that do I/O on behalf of some of their peers. So in this case, you can imagine that the way collective I/O might handle this write workload is that the green process would send all of its write data to the blue process, and then the blue process would write that all out in one big chunk. And you could see how essentially the blue process could write that out in one really big chunk that contains two processes' data. And what this looks like, we get 32 seconds of runtime and 268 megabytes per second. So this is a kind of a big improvement over no chunking, almost 5x, and a decent improvement over chunking itself, 1.6x. You can see maybe kind of counterintuitively that in this case, the performance is obviously better, but the number of I/O operations is still kind of high. It's not 256 like we saw in the last case. So you can see here there's about 8,000 accesses of a megabyte in size. And this is just an example of, this, like I said, it's not necessarily intuitive, but the MPIO algorithm knows that Lustre likes, single stripe size accesses, and tries to ensure that everything is basically a megabyte, and it kind of hides all the complexity of trying to understand what's the best access pattern for Lustre. And we can just kind of get it automatically just by turning on collective I/O, which is obviously really appealing. Kind of want to step through a couple of other example visualizations I've done in the past with Darshan data based on HDF5 applications. So this is based on a application benchmark called Maxio. It's a multi-physics benchmark that's pretty popular for HDF5. And so for this particular example, it's another kind of small scale 5-node 60 process using a single shared file. It's basically writing a 3D mesh about a gigabyte of cumulative data. And what we're doing here is basically we're comparing performance of collective I/O and independent I/O configurations, which was configurable for Maxio. You can see how drastic of a performance disparity this has just for this particular example. So there's an order of magnitude difference in performance with collective being much better. And you can see how we've kind of created a stacked bar plot here showing you how much time is being spent relatively on different aspects of I/O on each configuration. So on the left side for independent, you can see that HDF5 is doing a lot of work, and POSIX is doing even more, maybe even double or triple what HDF5 is doing. But essentially what's happening here is that HDF5 is trying to break down this data set into independent accesses, which takes it a lot of time to kind of enumerate through. And then also POSIX is getting a lot of independent accesses that aren't well optimized or aggregated or something like that. Excuse me. So it really just gives you poor performance. And in this case, you can see that there's almost no time spent in MPIO. It's barely even visible. And in this case, that makes sense because with independent I/O, MPIO is often just passing it off to POSIX directly. On the other hand, on the right side, the collective I/O bar graph is a lot different. HDF5 and POSIX are almost not noticeable. So HDF5 is not spending a lot of time trying to break this down into accesses, and POSIX is obviously getting much more performant accesses issued to it. And you can see that MPIO in this case is relatively a lot more part of the I/O runtime. In this case, that makes sense because collective I/O is kind of what's dominating here, but that's exactly what you would want in this case. So collective I/O is able to use communication to kind of generate really optimized accesses to the POSIX layer. So it's a trade-off that you're obviously really happy to make. Next, we'll look at just comparing different data set access patterns across different configurations. So this is basically the same benchmark, but I did 2D and 3D output and also varied the number of parts that are used, so 100K versus 200K. And essentially what these radar plots here are showing is along different dimensions in the data set, how much data is accessed for the most common access from these applications. So basically what this is showing you is, what is the shape of accesses that are common for Maxio. And what this could be useful for is to compare with potential chunk settings. So if you know roughly how much data is being accessed in each dimension by your accesses, then you could potentially optimize your chunk settings along those lines so that you can get better performance when getting the data. Thought it might be helpful to kind of summarize what's available to you with these different APIs in terms of a handful of different tunables, basically. So Hopefully by now you guys have kind of taken away that striping is something that you should definitely be concerned with on Lustre file systems. It's not tied to any specific I/O API. It's something that you just kind of have to generally be aware of. So that's a tunable that you have that you can take advantage of and use for any I/O API. On the other hand, alignment, HDF5 and PNetCDF both have the capability to automatically align your application data, which we've seen can definitely impact performance, but also can lead to larger file sizes. For MPIO, collective I/O specifically can be automatically aligned. So the collective buffering algorithm will take care of alignment for you oftentimes, but independent I/O is not the same. And for POSIX, I have a check minus here for POSIX because obviously you can control the alignment, but it's not, you have to do it manually, so it's not fun or something that you necessarily want to do. Collective I/O, as you guys I'm sure have picked up on by now, is available in MPIO natively and used by PNetCDF and HDF5. POSIX, obviously, as we've been complaining about loudly all day, is not have any collective I/O features. And lastly, chunking is something that's only available in HDF5 at the moment. So yeah, just another reminder to please use high-level I/O libraries where you can. They kind of hide a lot of complexity of these different tunables from you and just make your life generally a lot easier. So if you can help it, try to use those. So I want to talk a little bit about kind of adapting to a changing HPC landscape. So a lot of what we've heard about today represents very much like the traditional HPC stack. So big MPI applications using collective I/O and things like that. And this is variations on this stack have been deployed at HPC facilities for decades at this point. But as we've kind of heard hints about today, the HPC computing landscape is definitely kind of changing, even if it's a little bit slow. And this is occurring at both ends of the stack. So it's at the application level, and it's also down towards the hardware and storage software level. So at the application level, large-scale MPI applications are still very much the norm at HPC facilities, but other things are definitely gaining traction, whether that's machine learning, deep learning style workloads like TensorFlow or PyTorch, data analytics frameworks like Spark or Dask are increasingly popular, and even entirely non-MPI distributed computing frameworks that are somewhat popular in HPC like Legion or UPC. And so these different frameworks all have their kind of different ways of defining data models and their own mechanisms for managing distributed tasks and things like that. And so we wanted to be able to account for this in Darshan somehow, which is, as I mentioned earlier today, it's been very, it was strictly tied to MPI applications in the past. So we wanted to break that dependency so that we could use Darshan in more context. So starting in version 3.2.0, we can support instrumentation of non-MPI applications. There's a couple of caveats that I'll cover here in a second. But essentially all you have to do is set an additional environment variable, this Darshan enable non-MPI. And then when that's set, then Darshan will basically generate a different log for every single process that runs in that environment. And again, this extends Darshan to a lot of different non-MPI applications that are increasingly popular. So the caveats are for non-MPI version of Darshan, apps have to be dynamically linked. We're relying on some mechanisms that only work with shared libraries, so that's a definite requirement. And one additional thing I'll mention as a caveat is that this doesn't currently work on the Darshan install on Theta. I tried that last week, and that was the seg fault Rob mentioned. I'm not exactly sure what's going on there, but I was able to test and confirm that if you install your own specific non-MPI configuration of Darshan, that it does work. So I have some instructions here that you could refer back to if you're interested in doing this to get a Darshan non-MPI install set up. So this is all using SPAC, which simplifies things if you're familiar with it. But we'll try to get the system-wide issue sorted out in the meantime. Okay, so now I'll shift to the bottom of the stack and say a few words here. So obviously as applications change, so too does the underlying storage technology to kind of meet the demands. So nowadays we're seeing a lot more than what we've seen in the past in terms of storage technologies that are available to us. It's not just like all parallel file systems with spinning disks. So there's new hardware trends that are enabling lower latency, higher bandwidth devices that are available to applications. So some examples that we've heard about are burst buffers and also node local non-volatile memory. Those are all things that are increasingly available to HPC users and can obviously give you a lot of performance benefits. And obviously, built on top of this, these sort of hardware and architectural constructs are new storage services, so things like Unify and Deos, which we've heard a little bit about. So it's kind of related to that, but I wanted to briefly pitch some recent and ongoing Darshan developments that might be of interest. So all of this stuff here is either ongoing work or it's just wrapped up and made available in Darshan 3.4.0 version. That's not currently available on Theta. We're hoping to get that deployed sometime soon. So just keep in mind that these features here are either not available at all currently or not on the Theta version. So first is we've got a few different instrumentation modules we're thinking about. So a heat map module has already been made available in 3.4.0, and the idea here is that we kind of capture these histograms of I/O activity over an application's runtime. So if you recall, Darshan's traditional instrumentation just captures it captures a fixed set of data for every file accessed. So it isn't able to keep track of every single I/O operation and their timing, essentially. So this is kind of like a in-between for that traditional instrumentation and Darshan's full-on tracing. So it's able to kind of, as the application executes, it's keeping track of which parts of the runtime are being used to read and write data across different processes and across different APIs. PNet CDF module, this is waiting in PR on our GitHub now, so we need to get this reviewed and hopefully ready for release here in the next few months, but it'll be nice to have some more in-depth instrumentation for PNet CDF along the lines of what we currently have for HDF5, so we have more information closer to the application layer about what's going on. And this has been contributed by Waking Lau and Claire Lee at Northwestern. Deos modules are also in development right now. So we're developing Deos modules for both their file interface and their native object interface. So we're really excited to get that integrated into Darshan and to be able to use that to kind of better understand applications that are going to have to port over to using Deos on our upcoming system at Argonne. Another thing we're really excited about is PyDarshan, which is a Python-based Darshan log analysis framework. Essentially, in Darshan 3.4.0, we had our first release. It has what will be our replacement for the Darshan job summary tool I presented earlier this morning. I'd hoped to kind of base all of these slides and plots and stuff off the new tool because, like I said, it's nice and we're excited to switch to it. But I decided not to just because it's not available yet on Theta, and it doesn't quite have all of the plots from the old tool. So we'll stick with the Darshan, the Perl-based one for one more year. But we're looking to switch over basically completely sometime in the next, probably by our next release, we'll have the Python-based tools completely ready to go. And we're also looking at methods inside PyDarshan to automatically detect certain I/O behaviors and notify users about them. Because as you've seen through my, working through different examples here today, is that you do kind of have to have an ability to know what you're looking for in Darshan logs and detect certain behaviors manually. So we'd like to get to a point where this can be done automatically, and that Darshan tools could probably give feedback to users on potential tuning directions and things like that. We think that's definitely kind of a missing part for Darshan right now. And this, I'll mention this, a lot of the contributions for PyDarshan came from Nick Altry and Tyler Reddy and Jakob Lutgau. Okay, so I'll quickly go through some PyDarshan examples just to give you guys an idea of what the new tools look like. So traditionally, we've just had our C-based Darshan util library and tools that are based around that. So Darshan parser, Darshan job summary. It's obviously not a lot of fun to write analysis utilities that are C-based or that are kind of parsing text from Darshan parser tool and stuff like that. So we really needed a little bit more elegant solution for getting information out of Darshan, Darshan logs and into analysis tools, basically. So we decided to use something Python-based. And so we're using Python's CFFI module to provide bindings to our Darshan util library. And then we're using that to expose Darshan's log data as dictionaries and pandas data frames and NumPy arrays and things like that that are a lot more amenable to Python-based analysis. And obviously, we're hopeful this will lead to a richer ecosystem for Darshan analysis tools. PyDarshan rather is available on PyPy now, so it's something that you could go out and pip install Darshan now. It's the latest version, so you could use this version of PyDarshan to parse basically any log file currently. This is just showing an example of how to generate. So this is the example of how to generate a new job summary we have a new job summary tool that produces HTML files, like I mentioned. So this is not producing PDF summaries like our Darshan job summary Perl script does, but it's instead generating HTML code that you can open in a browser and have a look through the different plots and tables and things like that. Just kind of like a sneak preview of the different things that are included in there. One thing in particular I think is going to be really useful is based on the heat map module I pitched a second ago. But basically, this is this heat map in the bottom left is showing you across time and across ranks where the I/O activity was for your application. And so this will be really helpful to get your bearings whenever you want to analyze a Darshan log file to see which APIs were used the most. Were there particular spots in time, or were there particular ranks that had hotspots and things like that? We think it'll be a really useful way to orient yourself to the I/O characteristics of your application. The I/O cost plots that we presented earlier today that kind of show you relatively across different APIs how much time was spent doing different kind of I/O operations. We've got a new one in the PyDarshan-based tool that'll incorporate data from HDF5, and when we add modules like Deos and PeanutCDF, they'll be included here. Kind of the big issue with the existing Perl-based tools is that it's kind of gotten cumbersome for us to update it, so it doesn't have information from new modules like HDF5 and stuff like that. So we're kind of focusing that effort on the Python-based tools that'll eventually take over. And we also have sections for each different instrumentation module that Darshan has, so like a POSIX instrumentation module, MPIO, so on and so forth. We're capturing a lot more detailed plots and tables and things like that were in the previous version kind of all glommed into one section. So it'll be a little bit more clear about the behavior of different I/O libraries. Okay. So yeah, with that, I'll go ahead and wrap up. So hopefully that the material we presented today has been useful for you guys in kind of understanding what you guys have available to you in terms of storage resources and also tunables and things like that to get the most out of what is admittedly a pretty complicated HPC I/O stack. So some of the high-level takeaways that I hope you'll take away is that optimizing your workloads can be challenging, but as we've demonstrated here, you can get pretty big performance gains just by looking beyond defaults and things like that. Use high-level I/O libraries where you can. I don't know if we mentioned that today, but that's pretty useful. I'll restate it again. Don't count on I/O libraries or file systems to give you the magic parameters to get the most performance every time. They can't be perfect for everything, so they often do require a little bit of thoughtfulness to get the most performance. Darshan, we think, is a great tool for better understanding and navigating this complexity, and we hope you guys will have a closer look at the type of information Darshan can give you and reach back out with any questions or feedback or anything like that. We're happy to hear from folks that have experience using the tool.
Thanks, Doug.